Okay, thanks everyone. Today we're going to have, for this afternoon session, a continuation of our image quality and optical performance double sessions. We're going to get deep dives into a few areas that are contributing to image degradation in various ways. Yes, and so we're going to start with a talk by Gabriele about stray light in Rubin. Gabriele, do you want to share your screen?
Yes. Can you hear me?
Yes. Everyone else?
Okay, great.
Okay, great.
So let me try. Do you see my slides? Can you confirm that you see my screen, guys?
Yes.
Okay,
Yes.
great. Thank you. Yes. Good afternoon, everybody. Thanks for joining this session and thanks for having this topic into this workshop. So I'm talking on behalf of many people, which probably go beyond this list and beyond these groups that I've listed here. And I want to thank because it is really a teamwork, and everybody has been playing a major role in this in achieving these results that I'm going to show you in a while. So I would like to quickly introduce the concept of stray light for some of you that might not have big familiarity with instrumentation. I think it's a very nice definition to say that stray light is unwanted light that reaches the focal plane of our optical system. And it's quite interesting to also read a piece of this letter from the mathematician Euler, reporting basically suggestions to avoid the stray light to reach the focal plane of a telescope. And somehow the measurements or countermeasurement that is suggesting are still valid nowadays after almost 300 years, because it's suggesting and reporting on the necessity of blackening, of putting the lenses and the optics inside a tube, which shall be blackened, so painted with absorbing paints, in order to prevent unwanted light to disturb the representation of the sheen, as you reported here. And somehow that's not much more that we can do nowadays as well. And to give you a visual idea of what we are talking about, you can see the picture on the right. Some stray light from the sun. If we took a picture with a refractive optics camera, of course, with Rubin, we don't observe the sun, but we still have bright celestial objects like moons, like the moon, planets, and bright stars. And not all the optics of Rubin are enclosed in a blackened tube, and we know that physiologically wide field telescopes like Rubin are somehow prone to develop and suffer from stray light. The first evidence of stray light was found already back with the CONCAM on-sky commissioning, where for a relatively nearby region, immediately outside the outskirts of the focal plane, we saw in the presence of a very bright star appearing some rings, some strings of bright light that, as you see here in the image on the left, that we managed somehow to partially reproduce with ray tracing software simulation and study more in detail and kind of backtrace to a series of stray light reflection between metal and ghost reflection between filters and optics. And this was just the beginning. And of course, now having a much wider instrument, much wider field of view instrument, we see a wider collection of artifacts related to stray lights. Here I have reported a few of them, not a complete list, but somehow the most prominent or most peculiar that we have been observing and studying. For some of them, or for many of them, we know their optomechanical origin. We know where they come from, or we think we understood where they come from. For some of them, we understood also from in which of axis range they develop, not for all of them. And we know also that some of them will kind of self-resolve following the installation of the lighting screen. Here I just pause for a moment to let you check these images. You see the morphology is very different. You have very different extensions, very different appearance, let's say attributes. Some of them are structured, some of them are more localized, some of them are very wide. The workflow that we follow in the stray light working group is now consolidated. Somehow, of course, there is a phase where we classify, we spot the feature, we classify it based on some visual attributes that we start to know, and we put them in a kind of zoo in a Confluence dedicated page. And then we try to run some script that have been developed by Alessio and Luca, our PhD students working with us, that try to identify which could be the culprit, which could be the brightest objects nearby the line of sight of our telescope that could somehow create such a pattern. We have another tool that cross-correlates between the star position, the bright star's position, and the telescope pointing that has been developed by Alex Drika Wagner. And we have, of course, Batoid as a ray tracing modeler for geometrics optics that have been developed by Josh Myers that have been very useful to model some of them. And then as somehow in-kind group, we are kind of expert in using ZMAX in modeling this environment of optomechanical reflections, including the step file for the mechanical parts from the telescope and the camera, as well as their scattering and reflecting properties. And we have been starting as well developing some photometric measurements, some photometric estimates, for instance, to estimate the surface brightness of the extended features. And here is an example of all these tools that we have put in place. I want to show you a few examples, and I don't have the time to dig into all of them, but I will show you the most famous or prominent ones, let's say, starting from the so-called scratched tape, which is by far the most frequent stray light pattern that we observe, is related to a direct path from the M1, as we say. So it's basically a stray light reflection, as you see here on the right, that sneaks in between two baffles of the TMA, is reflected of the M1, and enters into the camera, skipping, bypassing the reflection onto the M2 and the M3. It lives in a region between 20 and 25 degrees of axis, approximately. And as I said, it's very frequent. It affects at least 6.3% of all the image frame we took so far. But this is a lower limit because this is the kind of brightest stars associated with the brightest stars. So we expect fainter scratched tape, which by chance we observe when we stack multiple images also from fainter stars. This feature, as you see here from a real image, can be multiple. It moves across the field of view with the LSST cam rotation. And it also manifests itself with a slightly different morphology, also had slightly different names, but somehow with a similar shape. And here you see a simulation which partially reproduces some of these patterns that you see on the left. We have been estimating also the surface brightness of such a feature, thanks to the works of Alessio and the low surface brightness group. Here you see in the table some measurements that we have been deriving from scratched tape coming from Alpha Centauri. This feature should spontaneously resolve upon the installation of the light windscreen, which is this orthogonal shutter with respect to the main dome shutter, which restricts the acceptance angle along the elevation axis of the telescope. But we also have been developing, thanks to the work of Alex and Josh, a backup or temporary plan and mitigation strategy that would foresee to extend by this amount represented by the orange half moons here, the mid-level baffle, in order to basically seal this little loophole where the light sneaks in and makes it to the M1 and the camera. And this could be, as I said, a temporary solution. In the meantime, the light windscreen is installed and completed. Another very frequent and prominent feature is the so-called L3, so the third length, the lens angel wings. It's due to a very subtle effect of refraction coming from the bevel of the L3. At the edge of the clear aperture of the L3, on the cold side, so within the cryostat, there is a little bevel, a little change of curvature that you see better here on the top, which has an effective focal length super short, which refracts the light and creates this peculiar double tail pattern that you see here in the real image. And we manage also to reproduce this in ZMAX with a synthetic simulation. It lives in a very narrow annulus at the very edge of the field. And the brighter is the star, the longer are the tails. And also there might be a variable length depending on where effectively the star hits specifically the part of the bevel. Here you see that is rotationally symmetric, so it's all around, because in the end the lens is rotationally symmetric, and we believe this could be potentially solvable with an additional buffer either within or around the LSST cam. Another one that is less understood and concludes a little bit the overview of the examples is the so-called L2 bananas, which is a feature that is backtraced to a reflection onto these L2 supporting pads that you see in this image that are metal plates, unfortunately shiny. Here you see Zemax ray tracing that shows effectively one ray around 6 degrees of axis hitting this pad and being ghosted by the L2 and made it to the detector. And here you see that we managed to reproduce partially this feature. You see 2 bananas here on the real image, and you see 2 bananas here in the simulated one. Although I have to say that it's still a bit unclear, the visibility range, it seems wider. There might be also components of stray light coming from in-dome stray light that makes kind of appearing the bananas. So this requires for sure additional testing. So coming a little bit to the synthesis, I think we have challenges and perspectives ahead. For sure, we have been putting in place a very extended test campaign dedicated to stray light, and this has been started back to the CONCAM and since the, say, very first few nights of the LSST cam when feature appeared. The situation is expected to improve with the installation of the light windscreen, certainly for what concerns the wide off-axis angles. And additional baffles might be installed, are certainly under study, both for the TMA and the LSST cam. I have to say that additional light might come, as Doug was inferring, also from the opening of the dome louvers, which are these openings here to vent the environment, the volume of the dome, and minimize the dome scene. And probably this might lead to some additional stray light that we might discover. So we need to continue studying this problem, to study the occurrence rates, evaluate the impact on the science, especially on the deep drilling field, on the alert systems, estimating the surface brightness, estimating the percentage of the area of the detector covered by these features, eventually evaluate the avoidance strategy to go around bright objects, and also assess what's the best amplitude of deterring steps to avoid, to cancel as much as possible this type of artifacts or minimize the impact on the alerts publication and contamination of the scientific images. So my take-home message for the Rubin community is certainly that, yes, there is an issue of stray light that has been discovered with the commissioning of the LSST cam, and probably is a little bit greater than expected. On the other side, let's say we have a very motivated and numerous working group trying to address this problem from very different directions, with optical expertise, mechanical expertise, both in data analysis and science performance evaluation. So it's relatively powerful, let's say, community. We also have an enthusiastic community of people spotting and reporting stray light discoveries in one Slack channel. And we have certainly an enhanced tool now of simulation, both for what concerns the ray tracing simulations and also the kind of ephemeris for this stray light visibility and reproduction on sky. So many of these features hopefully will go away, will vanish with the installation of the light windscreen, and some new ones might come upon the opening of these louvers. And in the end, we are seeking for short and long-term mitigation strategies and corrective actions in order to minimize the stray light feature that would survive the completion of the dome and the completion of the deployment of all the baffles foreseen. With this, I have finished. I'm happy to take questions. I hope it was sufficiently clear.
Thank you, Gabriele. Here.
Molto grazie. There are some features that you weren't talking about, which you'll see in this DMP1 data, in particular the ghost feature around all the bright stars, which we understand it's coming from the filter and it's not going away. So these are the ones we can get rid of, perhaps, but there are also some other features which are intrinsic to the camera.
Yes, that's a good comment, Robert. I didn't open to the ghosts because I was worried not to have enough time. But of course, yes, we also see ghosts that, as you said, are intrinsic of the refractive optics, and we were expecting to have them. Some of them have comparable surface brightness, so we can also probably recycle some tools to minimize the impact of those ghosts for what concerns tools developed for the scratch tape, I believe.
So as a follow-up to that, really, the simulations you've done here are just amazing, right? Better than just about anything I've ever seen in another telescope. Is there any thought of providing as a sort of a mitigation strategy, providing maps that you could construct from bright star catalogs, especially for these that you're never going to get rid of, that can be used essentially as science mitigation instead of operational or mechanical mitigation strategies?
Yeah, so actually, it was something that we have been discussing with some colleagues from Cordoba that are developing some kind of maps for this type of, let's say, artifacts removal. I think this would be a very interesting scenario for sure. What I'm a little bit obsessed, I have to say, is really to make faithful simulations for most of the artifacts. So that's, I think, is also a precondition to be able to test and verify a baffle concept before deploying it, okay, especially for what concerns the camera, because I want to be sure that if we make the effort to touch, let's say, to redesign, to revisit some of the hardware, it effectively is an effective solution that doesn't leave any corner for residual stray light. So for some environments, for example, around the TMA might be less critical. Into the camera is certainly much more critical. So that's having a very representative and faithful tool that can really match almost one-to-one what we see is a goal also for the baffle design. And in the end, it will be probably a good tool also to try to look into, stray light maps of that you cannot get rid of, but to try to foresee for a given asterism on sky what will be the stray light feature and orientation, and hopefully provide a kind of mask or whatever that can help, let's say. So it's something that, yes, it will be in the end in the workflow. Not easy, I have to say, because so far the simulation I'm happier, let's say, is about the L3 wings in terms of reproducibility. I think we miss a little bit still this interruption of the scratched tape in the simulation here, because probably we miss some mechanical components, but we're working on that.
Thanks, Gabriele. I think yes, let's thank Gabriele again, but maybe one more question while Brian sets up from Aaron.
Yes.
I've been meaning to ask you, have you noticed any extra stray light features at 10 p.m., which is when the day shift observers head down the mountain?
Good point. Yeah. Well, I think this question is better to ask to Alex, which is really, I think, the most careful observer in terms of what pops up.
Okay, thanks.
But I think somebody saw something kind of very fast changing, probably associated with some, outside dome lights.
Okay. Let's thank Gabriele again. Thank you.
Gabriele, would you mind?
It's filter dependent, Aaron. Filter dependent.
Gabriele, if you may stop sharing your screen, that'd be great. Also, thank you for joining us. I know it's midnight back in Italy, so we appreciate that.
Thank you. Thanks. So have a good continuation of the meeting.
Yeah, all the slides of this session are already on the agenda page.
All right. Are we good? Okay. This is just a lightning overview of hardware with respect to the thermal control and sensing of the environment around the observatory. So let's get right into it. If you didn't know, EAS stands for Environmental Awareness System. It involves 3 functions: sensing the environment, controlling the environment, and then also controlling other subsystems based on those aspects. And the most critical task, in my opinion anyway, is the management of what to do with the dome thermal environment during the day. So preparing it for observations that evening, and then also doing the steady state tracking of all the subsystems based on the ambient air temperatures around the observatory. This is an old diagram of how that architecture was set up originally. Most of it still applies. Some things have changed names. So the overall OCS was envisioned basically as the CSC architecture by the service abstraction layer communication. And under that is the EAS, which distributes and coordinates between the various hardware systems. The EEC, the environmental control of the dome, which is now called the HVAC system. There was also a component for the oxtail dome as well that we used to prototype this architecture. The DIM, which was mentioned before, is another component. The weather station, which is now subsumed by the sensor component, and that's called now the ESS, or the Environmental Sensor Suite. Yeah, it's one of the bullets there. Okay, so what did we actually do after all these years? We prototyped many of the sensors, and they're still deployed in the Oxtel dome. And then we transitioned a couple of years ago to deploying the set of sensors in the Simone dome. So now we have temperature, humidity sensors mounted on the main telescope structure. We have 6 RTD sensors, 1 per tangent link on the M2. We have 6 sensors on each one of the, 6 sensors on the hexapods, each 1 per leg, and 2 on the camera rotator located on the motors there. For the rotator. We also have the DIM and an exact copy of the DIM that is also designated for diagnostic studies, and we can move it around. So it's not a fixed location. The lightning detector is also for weather sensing. The all-sky camera also for weather sensing. The vibration monitoring system and accelerometers for further diagnosis of image quality from a hardware standpoint. Alana already mentioned that. And then we also have the thermocouple system on the M1, M3 glass. That's what we have now. Enclosure environment control system, like I said, is now called HVAC. We have set points, and we're able to monitor the airflow going through these air handlers. We have 4 on the 5th level that direct cold air up into the moving section of the dome, so around the telescope. And we run that all day, every day, and select the target set point for the evening conditions. Moving on to M1, M3, real cartoonish overview of what it actually does. So you have these fan coil units 96 of them inside the support cell. And those actually extract air from the honeycomb of the glass mirror, condition that to a very accurate set point temperature, blow that out into the air plenum of the cell, the actual volume of the cell, that gets mixed up. And because of positive pressure, it gets recirculated back up into the honeycomb. So in that way, we are only delivering very finely controlled air temperature through the glass cell. So that's the intention of that thermal system. And only recently has it become more more mature and stable, as many people have learned over the last couple months. Sometimes it works, sometimes it doesn't, but I think we're getting there. Then the other thermal system that most people may or may not, be worried about with respect to image quality is the top end thermal system. And that is essentially a closed air circulation, again, with heat exchangers, 2 of them, and they're here and here. And that has 2 circulation pathways, actually 4, but the 2 main ones that are symmetric, one is for the M2 cell, and that basically rejects the heat generated by the actuators that support and control the mirror shape. And then another pathway that goes around the camera utility trunk. So at no point should this air actually escape from this volume. In detail, it probably does. And for that reason, we want to have this system track the ambient temperature as well, so we don't get hot air blooms coming off the top end of the telescope, because it is in the center of the beam. So that's the ultimate goal of this one. The actual temperature control to be coordinated by the EAS. We've got still some development work to enable that, but manually controlling that set point temperature for this system has, I think, is been a long road that I don't think it's on the top of our list of impact to image quality. And I think I'm almost done. This might be the last slide here for the next steps. So we don't have any surface temperature probes on the telescope structure. That was originally intended to be in place by this time in commissioning. So we do need to install those still. We also need to get the louvers working, and that will happen in the next few months. At least a partial set of louvers will be able to be actuated at night. We also want to install the triaxial sonic anemometers to get maybe not a calibrated external measurement of the dome seeing or turbulence within the dome air volume, and as well as getting more air temperatures so we can gauge gradients within the dome air volume. There's also some control feedback features that we want to implement on the EAS side, control strategy over the louvers. So basically optimizing the airflow against possible turbulence being induced by that strategy. So that's an active field of research for these particular systems. So I think that's it. Oh yeah, and then this morning we got new plots. Thank you, Eric, for showing these. So here's an example of a sequence of 3 consecutive nights and how different the EAS system actually performs. So this is the very first night, July 7th. We hit the daytime target within a couple degrees, which is not great, but not terrible. But we weren't controlling the temperature of the M1, M3 mirror very well. So instead of being within a degree, it was within 5 degrees, sometimes 4 degrees. But at the same time, we were also changing its temperature as well. So we were in a extreme cold condition and then applying maximum heat throughout the night. And that was a very, very bad thing to do. And we saw the seeing, I was going to put the plots of the seeing throughout the delivered image quality of the science data throughout the night over this plot, but I guess that didn't show up. Anyway, it was very bad. It was 1.2 to 1.6 arc seconds that night. So don't do that. Got it. The next night, much better. Yes, we hit the daytime target like within a half a degree. And the mirror as well was 1 degree below almost the entire night. And we got sub-arc second delivered image quality that night. And then the opposite thing happened the next night, where the system was sending set points. We got the daytime target temperature completely wrong. That was off by 5 degrees in the other direction. So we were chasing the temperatures throughout the entire night. And the mirror never really settled into a steady state. And this again, maybe it wasn't as bad as the first night, but it was still pretty bad. So now I'm done. Okay, I'll take any questions.
Okay, wait, Colin has one. Maybe Kevin can set up while we get the question.
Are those last plots you just showed going to land somewhere that we can see them regularly? Because that would be a lot of fun.
I think we might work on getting them into not Rolex. What
Times Square, yes.
Times Square, yeah.
Okay, let's thank Brian again.
Would you like me to share the screen? Yes, please, Kevin, share your screen. All right. Hello, everyone. I'm Kevin Panning. I'm sorry I couldn't join you all in Tucson, but I'm doing my part as the skeleton crew, keeping the telescope running at night these last 2 weeks. For those of you who don't know me, I'm one of the commissioning scientists based out of SLAC, but living in Chile. In addition to worrying about the telescope performance and operations as a whole, I focus a bit on LSST CAM, DREAM, and DIM, which I will tell you a bit about today. So specifically, I'm talking about the Rubin Tower DIM. This is one of our 2 DIMs available. As Brian mentioned, we also have a portable one. The Tower DIM lives up on Calibration Hill, shown here in the right of this image, right of the Simone Survey Telescope. There's a few bits of instrumentation on Calibration Hill. We have the weather tower, the Tower DIM up here, Oxtel, and then DREAM far off to the right. Today, I will only tell you about the DIM. The DIM is a complete telescope, the smallest telescope in our observatory. It's a 1/2 meter mirror with a 60 hertz, 400 by 600 pixel or so CMOS camera. This sort of high image taking rate is how it does its DIM measurement, which is 2 images of the same star on its focal plane and watching them jiggle around to first order. Here to the right, you see as well in view of the DIM inside of the dome. So I'm proud to say we've been regularly operating the DIM for about 2 months now. The system has existed at the observatory for quite some time. I believe 2018 was when it was delivered. And it's been through a bit of intermittent operations for the last couple of years. It's been tricky to keep the system running because it's a small team keeping it limping along, mostly me plus software support from Brian Brundle. Thank you so much. And a bit of limited support from Brian Stalder and Carlos Morales. The sort of 2 months of regular operations is not a coincidence. It's 2 months ago or so, the system started getting manageable enough that we could devote some time to the DIM and make sure it's running. We're happy to see that there's live monitoring at night. Here's an example of the dashboard that the observers can watch. We have a few different telemetry parameters to watch. Most notably the full width half maximum, which is why we're interested in the DIM. It gives us an estimate of seeing, but also some internal diagnostics like the flux of the 2 different spots, as well as the Strehl ratios, sort of giving us a sense of the image quality delivered to the DIM. So what does seeing at the site look like right now? Well, here's a plot of the last month or so of seeing data. We're seeing quite a bit of variability on a nightly basis. The sort of moderate to bad seeing represented here is not totally inconsistent with the middle of winter on Pachon. You can see the DIM is mostly running every night. There's a few interruptions due to storms like here and cloudy weather here. There's also plenty of technical issues that sometimes take the system down and require manual intervention. But I'm happy to say the data is here and available for study. Some of the early studies I've been doing personally have been trying to compare the DIM measured scene with some of its internal image quality measurements. Here's a series of plots showing some of those. We have the Strehl ratios, which I mentioned earlier, a proxy for the quality of the spots on the DIM focal plane, and then the flux of the 2 spots as well. And these are plotted against the full width half maximum measured by the DIM. What I'm happy to report here is there is roughly no correlation with any of these parameters and the delivered scene measurement. This is what you would want and what has not always been historically observed with this DIM. So this is pretty exciting. The DIM is far from done or completely ready to go and just humming along. There's a lot of next steps, both in sort of the analysis and investigation of the DIM, as well as just keeping it operational. This group is probably more interested in the investigation, and I could certainly use a lot of help moving these things along. We're fortunate to have on Pachon another seeing instrument, the RINGS instrument by Gemini. DIM and RINGS often do not agree. This is a question we want to dig deeper into and see if we can better understand what's going on. As reported earlier in, I think this session, but it might have been the last session, the DIM sometimes reports much worse values than we see on LSST-CAM. This is a clear point that we need to better understand. There's also correlations between the DIM scene measurements and site weather conditions like wind direction, other things that we want to look into correlate. We should hopefully see that the dim is independent of most of these things, but if there is a dependency of its measurement on something, that indicates perhaps it's not telling us the truth. Another investigation along that line is correlation with the measured scene and some hardware issues. For example, the focuser is quite problematic and sometimes disconnects, which means you'll get more out of focus images. It would be nice to confirm that that's not impacting the scene measured. I'm also exploring some ideas of quick summary stats to give us a sense of how the dim is working at night. These need more thoughts. But that's about all I have for the presentation right now. I wanted to make sure that this session can help keep on time and I don't consume too much. So I'm happy to answer any questions.
Kevin.
Hi, hi. Can you comment more about this? I'm intrigued by these periods when DIM seems to indicate higher PSF than the LSST. I mean, is this like bistable? It either works or doesn't work? And if it's just less than sort of a continuum, how can I then ever trust DIM?
Yeah, very, very good question. I'm sorry, I really can't answer that. I've heard reports of the dim scene being worse than what we're getting from AOS, but I have not had time to follow up, nor do I have any examples of when that has happened. So it's hard to say if it's sort of an on or off thing, or it could be correlated, for example, just by the focuser, which would be a big concern.
So we do have some data for before LSSTCAM was running, when only Optical was running. And what we saw was that the DIM has strong dome seeing. So in times when the wind was low, that was when Optical would beat the DIM. So I expect that's what's happening here, but we haven't done that analysis yet.
Yeah.
Wind direction also matters. Good point, Brian. Yes.
Similarly, the dim, part of the idea of it is you have the two spots. So if there's any telescope shake, it should take that out. But if it's really windy, you might be shaking in a sort of non-uniform way, and that might be bad.
Hi, Kevin. Thanks for the for the talk. Nacho here. On the comparison with rings, is that sort of a bias, a sort of consistent bias that you see between both, or is like more of a scattered disagreement?
It's definitely more of a scattered disagreement, fortunately. It's not that dim is always better than rings or dim is always worse than rings. It's you can get either situation, and sometimes they'll even flip in the middle of the night. From discussing with some people, this isn't entirely unexpected. Seeing measurements being compared between different optical systems is not exactly precision. But yeah, it's still probably we're seeing disagreements at a larger scale than we would expect.
So if you may, Kevin, like another thing to keep in mind, and I'm not saying it's explaining everything, but those are different locations. And even between the calibration hill and the so like the Simone telescope, there's a height difference. So something that we need to keep in mind is a ground layer and the wind and how those two flash. There's a strong wind between the two sites, even calibration and again the Simone. So it's not as straightforward as saying, oh, there's a problem with the DIM. It could actually be working really well. But again, it's not the same height. There's ground layers. So the one thing that we're looking with the rings is what is in a free atmosphere, compare it with the AOS blur. And for Optical, we've started to really look at what the DIM gives, what the Optical gives, and what the Simone gives, and kind of try to do correlation between all those measurements.
Yeah. So supporting that too, the Rubin DIM gets the full brunt of the predominant wind direction. It's on a very windy site. To my understanding, the rings instrument is largely shielded by Gemini. And Gemini blocks most of the wind that it would normally get. So that could be one factor.
Kevin, thank Kevin again.
Thank you all.
Next, we have Johnny Esteves. Johnny, do you want to share screen?
Yeah, I can share screen. Just give me a second. Hello, everyone. Can you see the screen? Yes? Okay. I'm Johnny Esteves. I'm a postdoc at Harvard working with free stubs and Elana. And today I'm going to talk about LSST cam guider sensors and some early analysis for Rubin nighttime operations. The guider comprises of eight sensors that are 4K by 4K. They're located in the corners of the focal plane. So you get the entire field of the LSST cam in the corners. And each was designed to operate at 9 Hertz with a window size of 50 pixels by 50 pixels, basically 1 star in each of these square. But currently it's operated at 2 Hertz, basically 2 more or less steps per second, and in a window of 400 pixels or 400 pixels. The integration time is about 50 milliseconds. And here you have an example of the data that is taking, and it's 400 by 400, as I said, and you can also see the star field with a bunch of stars. In some sensors and other, you don't see many stars. The fields are not being selected, so this is random fields, and in the future it's gonna select 1 star and focus on that star. And why the guider diagnostics matters? It's gonna be used for performance diagnostics, but it could be improved and could help in the future. It could be used for guiding too, guiding the telescope. For now, we can use for the server performance, image quality, and guiding stability, like track drift, jitter, and other telescope mount issues. And since the guider sensors are located in the focal plane, it provides good centroid and flux measurements of the field of view that the LSST is taking. So we can also monitor clouds and scintillation and the same at that location. And most important now is that we're gonna have rapid feedback during the night operations with Rubin TV. And if you have seen Rubin TV, it looks like that. And soon we're gonna have 1 more box for the guider, and the guider diagnostics are gonna be deployed in real time and also as a nighttime summary. And it's gonna be aimed at observing specialists, commissioning scientists, and support staff. And these are some of the key metrics that we're gonna include: drift rate in the 3 in-out as and the total, and the standard deviation of the centroids, something that Jack is going to talk more about in the next talk, the flux difference, and the full width half maximum. And here I have an example of a GIF for 50 steps, and basically you see that the telescope was drifting and the star was moving across the focal plane. And in these GIFs are going to be produced forever image. And although it's not integrated to Rubin yet, Rubin TV, you can already make these plots just like downloading the Sum 2 tools and putting this branch, and with few lines, you can start making the plots. And here it's another example of the plots. The centroid offsets here are basically the position minus the median of the 50 steps in a elapsed time of 30 seconds. The plots have different markers for different guidance sensors. So basically you're seeing here all the stamps with all the guiders. And I implemented a linear fit that's robust against outliers. So the blue points here are outliers. And on the top, you can see what is the slope, the scatter around of this linear relation, and what is the significance of this slope in relation to the scatter. So it's about of the significance that is basically the t-value of this linear fit. And you can see that there is drift. We also saw on the last image, but it's worth to point out that the scatter is related to the jitter of the mount and the atmosphere. And the telescope drift is related to more low frequency time variations, like the telescope tracking errors and point model errors. And you can also look at these plots for PSF, flux, and ellipticity. And here an example of the local measurement of how much the PSF changes during an exposure. And this is a very preliminary result, but here I basically computed the drift rate for 4 nights very recently, past week. And this data is more than 1,200 exposures. And the drift rate here is the absolute value. And you can see that we have very large drift rate, something that is not expected. And it's about 0.2 seconds per exposure half of the time. So it's larger than this half of the time, sorry. So this is something that should be, this already shows the importance of the guider as a way of diagnosing what is the telescope drift and the mount. And one way, although this number, it seems high, to make the conversion to the PSF, it's not very straightforward, but we can do a back of envelope calculation, just assuming that the center is moving with a constant velocity and calculating the variance, you get the drift, the sigma of the drift should be square root of this number and divide by the should be this number divided by the square root of 12. And doing that, we can estimate what is the impact of the full wave half maximum for the spec of what we would like to achieve with the image quality budget. And we are sheer far from achieving that. And the median value is 0.2 arc seconds per exposure. So the drift it's causing, this is a non-negligible contribution since the imposed requirement is 0.025. There are some outliers, and we have a very big tail here of outliers that can be related to telescope tracking or point model error. I'm not sure. I was trying to investigate, so I made some basic plots of the mean drift rate as a function of alt-as to see if it's something related to the mount. And you can see that at low elevation, you see the telescope, the tracking, the drift going up. And at high elevation also, it tries to go up. But also you see a trend with azimuth. So in the southeast direction here, in the east direction, you see always a red. And then in the west direction, blue. So something's weird. I'm still not sure what this means. And with our deck, that could point something related to the tracking error and the pointing model somehow. We don't see very strong correlation, but we see that low declination, you have some high drift rate. So Here it's an example of a bad case, and things are, for me, we see a very strong slope, and it's much higher than the scatter of the relation, which is the turbulence and the jitter. And I'm trying to make some diagnostic plots, and the first that I come up with was to basically plot the slope divided by the scatter. So try to see what dominates, which are the exposure that are dominated by the drift, and which one are dominated by the atmosphere. And we can see that the drift rate outliers are dominated by high elevation and high rotator with mean square error values. So this something could be related to the rotator. More to be investigated. This is still a very preliminary plot, so let's see. And one thing that I should mention, that at low elevation you have more atmosphere, more jitter because of the atmosphere. And this is my summary, and the guiders matrix, it's already proving its value, and soon we're gonna all have access into the Rubin TV. You can also access the notebooks here. And next step is to complete the deployment of diagnostic to Rubin TV. We're going to investigate how the centroid matrix relates to environmental data and use these guided central. And the next talk with Jack is going to talk more about how we can use these to measure the scene. Thank you very much.
Thank you, Johnny.
So Johnny, of course, thank you. That's really interesting stuff. The effects of drift, right, are non-axisymmetric. So I think it begs the question about what impact do your measurements have on what we've been seeing in our data for as far as ellipticity of the PSF goes, right? So one way to do that, since ellipticity is going to be PSF size dependent, just pick a fiducial PSF size and calculate the effect of ellipticity then for the amount of drift you see, and see how that correlates with the ellipticity we actually measure.
Yeah, that's a good test. And to be honest, this was my first week like reading about the topic, because I didn't know that the drift could impact depending on the direction on the ellipticity and the PSF. So I'm still trying to understand how I can improve this model here and how we can correlate the drift and the direction of the drift with the PSF and the ellipticity. And that's something definitely that we should look into in the future.
Thanks, Johnny. If Jackie wants to share screen.
Sure. Yeah. Okay. Let's see. Okay. What do you see that? Okay.
Now we see it.
Yeah. Okay. Hi. I'm Zhuoqi Zhang, Jackie. I'm a graduate student at Stanford, working with Aaron and a lot of other people on the commission team. And yeah, as Johnny said, I'm gonna talk about how to use LSSC camera guider sensors as an atmospheric sea monitor. Yeah, so the first question is, what is atmospheric sea and how do we measure them? So basically, when we have a light coming from an infinitely far away source, the incoming light is basically plane wave. But as it enters the Earth atmosphere, it gets perturbed by the atmospheric turbulence. So accordingly, when the photons gets into the telescope, the incoming direction is also slightly perturbed. according to the perturbation of wavefronts. Those photons would land on slightly different places on the focal plane. So as a result, we have two effects. The first is that it smears the image, and that is known as the point spread function, the PSF. And the other effect is centroid motion. So if you look at a star at some instantaneous exposures, you'd see that the centroid would move and like the jitter. So Kolmogorov and von Karman have studied the atmospheric turbulence a lot, and they have given us a form of power spectrum of the atmospheric turbulence. So using the Kolmogorov or von Karman power spectrum, we can relate the PSF size with the centroid motion of the star. So that is what the first thing that we can do with LSST CAM. So because the measurement from centroid motion to PSF size would require fast or instantaneous exposures, and preferably at high cadence. That is exactly what the guiders can do. So the first thing we can do is just to take the RMS of the centroid motion of guider stars and to infer atmospheric seeing, or the PSF size. So this is closely related to DIM, the differential image motion monitor, as Kevin introduced, and the principle at least is well tested before. So it turns out we can do a little bit more than just measuring the total atmospheric seeing. So imagine if we have a pair of stars or two stars, two guider stars. If we look at the air columns, the air columns of the two stars will overlap very much at the bottom or near the ground, as shown in this diagram. But the air columns would be separated further away at higher altitude or at the free atmosphere. Yeah, so that means the air turbulence near the ground layer would introduce more coherent centroid motion. So the centroid motion due to the ground layer would be more correlated. But on the other hand, at the free atmosphere, because the air columns are separated further apart, the atmospheric turbulence would introduce uncorrelated motion. Yeah, so using that, for example, on the left panel here is the lower panel is a diagram for two stars that are diagonally apart in the focal plane. So if we measure the common mode of the centroid motion, or more precisely, if we measure the covariance, this can give us an estimate of the ground layer turbulence strength, or more precisely, it is the weighted average of the turbulence strength according to this solid line here, and it gives roughly ground layer turbulence strength up to 400 meter along the line of sight. And if we take the differential motion, or more precisely, the variance of the differential position of the two stars, it will give us the free atmospheric turbulence strength, or more precisely, the weighted average of the turbulence strength according to this dashed line. So now, if instead looking at more closely separated pairs, so that is if we look at the stars in guiders that are adjacent to each other, it will be able to probe the ground layer, or to probe the common mode would be able to probe atmospheric turbulence strength to a higher altitude, roughly 2,000 to 3,000 meters along the line of sight, and it will also probe a higher altitude of free atmosphere by looking at the differential motion. So combining these, we can basically do a layer separation, and the goal here is to separate out the 2 or 3 layers of atmosphere, and hopefully we can look at the ground layer and tell what's the ground layer and dome contribution look like, and hopefully understand the impact of the dome environment on seeing. Okay. Oh, so yeah, so this is the eventual layer separation that I was able to get at. So basically, I can separate things into the scene into 3 bins. For each bin, we can have a measurement of the turbulence strength, and that measurement of turbulence strength is basically the weighted average of atmospheric turbulence strength according to these curves shown on the right as a function of height. Yeah, so we have a ground layer roughly up to 250 meters, a mid layer, and a free atmosphere layer that's roughly about 500 meters. I've also included some model error here just to illustrate how much theoretical uncertainty there is in these measurements, and that's mostly because we don't know how well the atmosphere would follow, say, a fiducial von Karman or Kolmogorov power spectrum. Okay, but anyway, I was able to apply this method to some of the existing LSST GAM guider data, and this is the analysis of one night, so that's the June 19th. What is important to look at here is first of all, the red curve is the measured full width PSI full width half max on the science sensors across the entire night. Now, the gray curve is the total seeing inferred from the guider image motion alone. But to sort of predict the overall seeing, we have to add the AOS residual contribution. So that gives the black curve. So the black curve is the inferred total PSF size, and compared to the red one that we measured on the science sensors, we find that they correlate kind of well. So furthermore, I was able to set, using the layer separation scheme that I described before, I was able to separate 3 layers of atmospheric seeing. So the blue one is the very ground layer, the orange is mid layer, and the green is the free atmosphere component. So on the top panel, the green, orange, and blue add up to the gray, the total atmospheric seeing in quadrature. And for the bottom layer, it is the relative strength or relative contribution from each of the layer. So you can see some variability over the night. So now here are some of the comparisons or validation tests that I've did. So the first one, the left one is the delivered full width half max versus the inferred full width half max only from the guider's star-centered motion. So you'll notice that they don't correlate well, and that is, one possible reason is just the theoretical uncertainty on the turbulence power spectrum. But still, you'd see that they follow sort of a correlation. The correlation coefficients between the delivered full width half max and the inferred full width half max is about 0.5. And on the right is to more of testing the layer separation scheme. So I was comparing the free atmosphere seen inferred from the guiders versus the free atmosphere seen measured on rings at CDIO. So CDIO is about a few kilometers away from Rubin, and rings is the separate atmospheric monitor instrument at CDIO. Although they are separated by some distance, we'd expect the free atmosphere to not differ that much. And here we actually do see a rather tight correlation between the guider free atmospheric seeing and the rings free atmospheric seeing. Yeah. So, Craig. Craig, you're muted.
You say CTIO, but you don't mean that, right? You mean Cerro Pachon.
Oh.
CTIO is 10 kilometers away.
Oh, okay. Oh, I guess I was confused by the name. And
Jackie,
yeah,
it's on Gemini, just so you know.
Oh, okay. Okay. I saw Kevin had a hand.
Oh, I just wanted to comment, CTIO does have a
Oh.
rings instrument, so it's important
Oh,
to be
okay.
clear which one you're
Oh,
using.
sure. Yeah. Okay. Yeah. Then it's Gemini. Sorry for that. Okay. So now back to the guider analysis. So here is what we're trying to look after was the ground layer scene, and here is a histogram of the distribution of the ground layer scene, so that we infer from the guider. So on the left is the relative ground layer turbulence strength compared to the total turbulence strength. So it should be the fraction of total turbulence strength coming from the ground layer. Yeah, so the mean and median is just below 0.2, and I comment on that there are some negative values here, which are due to stochasticity, because in sometimes you might just have negative correlation due to chance. And on the right is the histogram of the ground layer scene full width half max in arcsecond. Yeah, so mostly it's below 0.5, the mean and median. And finally, here are the contributions here. And finally, here is what I try to do to figure out what are some contributors to the ground layer or dome scene. So I was plotting the ground layer scene inferred from the guider with a number of telemetry. So including humidity, pressure, wind speed, and versus a number of temperature readouts in the dome. So for most of these telemetry, we don't see a clear correlation except for wind speed. So here are some weak correlation that when the wind speed is high, we also tend to get worse ground layer scene. And yeah, I think that will conclude my presentation. So for the next step, we hope to use some perhaps more sophisticated machine learning methods to study the ground layer, how the ground layer scene depends on telemetry. So maybe that will give us some handle beyond the linear relationship. And all these analysis, as Johnny already mentioned, will be done in real time and hopefully report to Rubin TV soon. Yeah, so that's my
Thanks,
presentation.
Jackie. Unfortunately, I don't think we have time for questions.
Okay.
Sorry. Craig, could you share slides and present?
Sorry, I forgot to unmute before I shared. Let me try again. Okay, can you see this? No, are you hearing me?
We can see and hear.
Craig.
Yep.
Okay. Okay, good. So, yeah, I'm Craig Lage. Sorry I couldn't be there. For most of you know, but I spent 4.5 years down in Chile helping construct the observatory. But in May, I moved back to California. So, but I'm continuing to work remotely. And what I'm going to talk about today is we've been generating plots in the Rubin TV to look at the impact of the telescope, the mount and the telescope, not the optics, but pretty much trying to look at everything but the optics, the impact on the image quality. So this is some of the initial plots from almost 2 years ago now. And so just to show you what's plotted here, at the top we've got azimuth. This is an exposure. So the top is the azimuth and elevation. The bottom is the torques. And in the center is the error. And the error is basically the difference between what the mount encoders are measuring and what the commanded position is. And so it doesn't capture, for example, top end vibration, which doesn't impact the encoder. It doesn't capture pointing errors because it's just how well is the TMA doing what it's told. And these glitches were in the initial plots, but they've since been fixed. And so then this is, a year later, we had added the rotator by then. So same plot on the left, but now we have the rotator. And you can see these large rotator tracking errors, about a half an arc second. And it's caused because the rotator is gear driven. And so there's an error as the gears rotate. And it seems bad, but on the right, you see that basically a 1 arc second rotator error leads to an image error of 0.04 arc seconds. So this half an arc second rotator error is 0.02 arc seconds, so it's negligible. But you can see, even though we're primarily looking at the encoders, it does see things like wind speed. As one thing we've seen in the Oxtel is it's very sensitive to wind speed, and elevation is worse. It's up there as the wind pushes around the top end, especially in elevation, because that's the direction the slit is open. So you can see on the left, a low wind speed, and on the right, a high wind speed. Still 0.04 arc second total RMS error, so still small, but you can see the wind speed. Everybody still with me? Can you still hear me? Just like to confirm once in a while. Still hearing me, right?
Yes, we can hear you.
Okay, thank you. And then here's an example where these plots caught a problem, where you see these glitches on the left. Periodically, you can see these glitches in the mount error and in the torques. And they were tracked down to an error in the commanded position, which was diagnosed and fixed by Tiago, was causing by the pointing model losing contact with the weather information. So, it was definitely valuable there. And so, and then this year we're still not catching some failures. For example, on the left here with the magenta circle, you see it gave a very small image impact RMS, less than 1/100th of an arc second, but the image on the right looked like that. And basically the reason is because the rotator in this case was tracking what it was told, but it was still settling basically when the image was taken. So what we did was we added basically an estimate of what it should be doing based on a simple linear model of alt-az and rotator. And so on the left is an example where it wasn't tracking at all. And so said the image impact was good because it wasn't tracking at all, and it was doing what it was told. But on the right is after we added that model of what it should be doing, now the image impact is large. So that was that fixed a bunch of these where we were seeing bad images, but it wasn't catching it. But after that, we were still seeing failures like the one on the right here, where the image looked like this and the image impact was, 0.005 arc seconds. So we added the rotators, the cam rotator on the top and the M2 rotator on the top. And you can see what happened to cause this was that the M2 rotator was making big changes in the middle of the image. And that caused the image to look like on the left. And so here's the current status. We have the the Azinel on the left, rotator in the middle, and the hexapods on the right. And the total image impact is including all of those. And The hexapods are currently being intentionally moved during the exposure in order to keep aligned with the lookup tables. This 0.07 arc seconds here is not currently subtracting off the lookup tables, so that's some work in progress. There's still discussion of, there's kind of two schools of thought on whether we should be moving the hexapods while exposing. One idea is we shouldn't move things while exposing in order to keep things as stable as possible, and the other is we should move the hexapods to follow the lookup tables. Ilana ran a test comparing these two a couple of weeks ago, but the results were inconclusive. So we want to repeat that on a night with better seeing. And so here's some of the current issues. One is we still have some ones where we take an image when it's not exposing. We'd like to get rid of those. We have some where the mount stops tracking in the middle of exposing. Sometimes it does this when it faults, but it also does this sometimes when there's no faults. It just, for some reason, well, for reasons we understand but haven't fixed, it stops during the exposure. And then we have these ones like this that are large hexapod motions during the exposure, and so the images look like that. And actually, if you look, well, let me. And so, summary is that the plots have been proved very useful, and they're currently being generated for every image in Rubin TV. So, let me try and show you that. So in Rubin TV, here's Rubin TV. It's the blue one here, the mount torques plots. And this mount motion image degradation, this column here is the column there. And so here's a bad one, this 5, where it's 5. And it's one of those where the hexapods were moving during the exposure, and the images look like this. But beware, because this said that the PSF was 1.09. So if you're doing a cut on PSF, you would include this one. Okay, that's what I had. Any questions?
Awesome, thank you. Maybe we can take a question while Tom sets up. Any questions for Craig?
Hey, Craig, so have you identified like the key metrics from these plots to be able to send those to ConsDB? So maybe we can flag them as bad before we even try to analyze them.
That's this column here, the mount motion image degradation, which includes all components, the TMA, the rotator, and the hexapods. There is a schema in ConsDB, but the data is still not being sent to ConsDB. And I've asked a couple of times why, and I still don't have an answer as to why it's not being sent to ConsDB. It needs to be so we can do cuts on it.
Okay, positive progress. Thank you.
Yeah.
Thank you, Craig. That was, we will also get it in ConsDB.
I know Alana is working on trying to get it in ConsDB. Thank you, Alana.
Now, Tom.
Okay, hi everybody. Sorry, I get the unfortunate pleasure of keeping you from the end of the day, but that's how the schedule works. Can we get rid of the little guy? So I'm going to talk to you today about something that doesn't actually involve either image quality or optical performance, because it is, as the tech note that I managed to sneak out earlier this week says, determining the astrometry using these science pipelines, but with operations rehearsal data. So none of this involves any real pictures, but hopefully the results will be interesting to some people anyway. Of course, we call these things photometric catalogs, but half of the things you get out of them is astrometry. You get the position and the covariance of that position of all of the objects in the sky. So I happen to have a nice picture of Y is there. And you've got a bright source, you've got a faint source, they have their corresponding uncertainties, which I will represent with this small dot and nice rainbow circles, respectively.
Sorry to interrupt, but you need to share the screen so we can see.
We are sharing screen. I think someone else is still sharing screen.
No.
I think Craig might need to stop to ping it, but you
No,
can also
I-
click the.
I still.
Okay, all right, it is working. You're supposed to be seeing a nice picture I've made, a little schematic of that pixels in the red lines. If you're not seeing a little picture of red lines with a reduced chi-squared plot in the inset, then you're not looking at my slides. As we go through a cut of the image on the bottom there, we least squares minimize, we maximum likelihood fit, and you essentially move your PSF around in position, and then your chi-squared minimizes at some best fit place. And it's the error bar that is my rainbow circle, and the best fit is my central point. And we represent these as most things with a Gaussian approximation because it's good. And then these go into things like you use them in proper motions and parallax fits, and you get your position and your uncertainties, and you fit for the higher order information. But also, as is my work separate from this, deriving the counterpart associations. So you take your orange square in the middle there, and you want to know which of those other rainbow circles is the correct counterpart from LSST to, say, Vista. And you need to use the uncertainty information in these images in the catalogs to do that in a robust way. But we want to verify that these positions and precisions are both correct, that they're both in agreement with each other. And one way to do this, as I said, you get a covariance in the catalogs from this maximum likelihood fit. But there's also what I'm referring to as some sort of scatter sigma. There's a standard deviation if you take repeat measurements of deviations away from true. You will build up a plot in the middle there of some delta right ascension and delta declination, which again, we assume follows some sort of Gaussian, which in these plots will be represented as Rayleigh distributions, which is just a integration around 360 degrees to convert to one dimension, both because then the plots look nicer because they're one dimensional, and that's how screens work, but also because we have other aspects of uncertainty I don't have time to talk about here that are circular. So for other work, TBD, the circularization becomes necessary. But if we had two data sets, one in this sort of orangey yellow, depending on your screen, and one in the blue, and we could get the separations between pairs of objects we know are the same, then those separations become our scatter, and the quoted catalog covariances become our covariance sigma. And then the ballpark, the game just becomes plot covariance against scatter and control for things like magnitude, signal to noise ratio, position on the sky, see what you get essentially. And that's what I'll walk you through now. But of course, I've said deviation from true, which is quite hard to do because we don't really know where all of the stars in the universe are, because our jobs would be quite a lot easier if we did. So we would use something like Gaia, which has a higher precision in its astrometry than LSST. So we would say that the deviation from true was Gaia minus LSST. And sort of people take Gaia to mean truth quite a lot these days. It's become a shorthand, but we don't actually have to do that. We can do one better because Operations Rehearsal 3 was a simulation of a few nights of LSST. So we do literally have truth tables. So we say, well, actually, that's fine. That solves this problem. And that's why we're doing this test with the operations rehearsal data rather than data preview data, which we actually have now. But for an example, we're in the source table. So this is single visit reductions for the RA of 250 declination of 2 pointing that was simulated at just shy of 23rd magnitude. The error bars in the background are these truth table minus simulated catalog separations, binned up as standard in, it's a histogram. And then what we have is we have two different histograms. Ignore the red for the minute. We have the black line and we have the blue cyan line, one of which represents the uncertainty if we were to use the quoted catalog covariance, the catalog pipeline derived uncertainty, that's in the black line. And then we have the scatter is a best fit to the black data, essentially. We have the scatter, the best fit to the error bars. And we can see that those numbers there are almost the same. They're just shy of 4 milliarc seconds each. So that's good. We can say that the positions and the quoted uncertainties are in agreement. And if we then go to brighter uncertainties, we find that the quoted catalog uncertainty in that black line is too small to explain the scatter, which makes sense. There's some systematic uncertainty missing, some sort of world coordinate solution systematic that we're not including in the data because it's a statistical covariance. That's all sensible. If you then speed this along and do all of these simulated pointings for all of these magnitude cuts, then you see something like this, which is a perfectly reasonable thing, as I said. In the faint, at faint magnitudes towards the top right of the figure, the uncertainty as the pipeline derives and the scatter of the positions, the standard deviations agree. And then there's some sort of systematic flaw at these bright uncertainties, bright magnitudes, which we can then take further. We plot some hyperparameters. We say, okay, we add in quadrature this systematic with some slope parameter. And then as a function of sky position, they're plotted on the top, and as a function of density on the bottom. And it's a several milliarc second systematic uncertainty that we're adding in quadrature with about a slope of 1. And these numbers are in agreement with prediction, but that makes sense because these are simulations. So the whole thing sort of is confirmed in a cyclical fashion. And then we can move on to the object table, but now we have to deal with the tracts because, of course, the sky gets broken up into this grid. And because everything is fainter, we're now at 23rd magnitude, here, 22.5. And here we see, again, essentially the same thing we saw before, where the cyan line, we have to fit the scatter of the data is slightly larger than the pipeline-derived uncertainties. That seems like something we saw before. But now, at 25.75, just shy of 26th magnitude, we see the opposite problem. Everything else I said before made sense and was not particularly interesting. It just confirmed our results. The reason I'm here today to try to give this talk is this figure, because that doesn't make sense. You can't have negative systematic uncertainties that you have to subtract in quadrature. So if we plot, again, all object table valid tracts for all of these magnitude slices, you get a power law in the function of the covariance as quoted by the catalog, its dependence on the scatter of the separations. And that number is 3/4, maybe it's 1/√2. I get suspicious when I see numbers that could be √2 in things like astrometry. And just to confirm this, we did a smaller, simpler test where we binned all of those tracks together. We had to account for the varying magnitude to signal to noise ratio dependency for things like sky background. But that allowed us to fit for a systematic flaw, which you can't see in the previous results due to number statistics. But you get a sub-milliarc second systematic, which is nice. Back of the envelope agreement between that and the scaling we saw for the source tables. But we confirm this power law slope, as you see in that red dotted line. And essentially, we can't explain this ourselves. So this is why I'm trying to give this talk. We control all of the things that we can control. The covariances as quoted, the magnitudes, source density if necessary, everything is held fixed as it should be for a good experiment. False positives are accounted for in our fitting process. The source table analysis works well and agrees with the predictions of the LSST science driver paper. So therefore, we think that our analysis is essentially proven by that, and therefore there's a question mark over the object table analysis. But we did know that we had to hold the number of visits approximately a constant due to the dither pattern, but we account for that as well. The photometry is good. There is a tight monotonic relationship between signal to noise and magnitude, once you account for the visit problem, as I just mentioned. And the bright source statistical uncertainties look good based on the relationship between statistical astrometric uncertainty and seeing. Yeah, I've quoted Ivan King, 1983, as the citation there. But I should note that this is aperture photometry magnitude, specifically APO3, which may hide second order problems with things like covariant and with variance propagation in the coadding process. But that the essentially the data in the bottom, the histogram in the background, agrees with sensible values for seeing of slightly sub-arc second is probably what was simulated. And I will just end there with that bold point of what's up with this figure. Please, somebody tell me what's wrong with this figure. Thank you.
Hi. Did you try to correct atmospheric turbulence that are in this simulation?
I did nothing because I just took the data that you lot made and I plotted my plot. So
Yeah, because like I mean, like, I guess we already discussed about that, but like the floor like is consistent with the atmospheric turbulences at the visit level. And like I know like Claire Sanders from this data set, she made some plots at the visit level, and you can see clearly like you have like what you expect from atmospheric turbulence, and this is not yet corrected in the pipeline.
But would that not affect the source table analysis as well?
It will, I mean, like
the source table worked very well. The data are great. Good job. There's something going on with the co-adding because everything that the source table analysis, that's all incredibly consistent and tight and good and A+. But this specifically, because it's at 26th magnitude, yeah, we go all the way to the completeness limit of the table.
You see no shift in any of the single frame images?
I see no images. I see tables. I just have the catalogs. I can't do this, but also there's problems with operations rehearsal 3 anyway.
So for the dimmest sources in the simulation are handled differently than brighter sources.
Okay.
But we don't do anything so basically what happens is we treat them more simply in terms of their SEDs and in terms of how we put them on the sensor. So that shouldn't shift them around. But what is true is in those cases where they're most dim, it's only a few photons, right? And this operations rehearsal, I think we simulated for 5 nights, but we only used 3. So it's something like 3 nights of data. So I don't think any of the coads are going to have that many visits associated with them in any particular place. That would be an interesting thing to check. I don't know. If
Yeah,
it's in the table
I'd love
or
to
not.
do operations
So
rehearsal N+1.
you should
Yeah.
try to figure out how many visits are in the coad, because with only a few photons that are showing up,
80.
Statistically, the chance that you're going to wind up right at the center of the centroid is actually quite small, and especially if you fold in the shifts that come from the atmospheric turbulence. Somehow it's not surprising to me that statistically you could be off.
I'm taking the central core of this basically, and that's 80 visits.
If it was me, I worked on the simulations. I would go back and I'd try to pull the images and look at them.
I don't know how the simulation was done, like, but in real data, like you have a main wind direction, so it's unclear like how it cancel out from. Okay.
Yeah, I think what Pierre-Francois said about the turbulence makes a lot of sense at the bright end, your systematic bright end uncertainty that you're seeing, which makes sense.
Okay, yeah, it could be that. My go-to example is WCS, but sure, it could be that. But that's the floor. We like the floor. We can explain the floor.
Right.
The floor's a good number.
So, yeah,
it's the
so-
slope.
Yeah, so I'm not really sure what I would expect from coad astrometry at the faint end. I mean, like just honestly, it's.
But it's not at the faint end. It's the whole thing. That's what.
Well,
10 to the
we
minus
said
3
that-
arc second precision is still subject to the power law. And then it.
Well, we said we understood how we can deviate at the bright end. What you
Mhm.
don't understand is the deviation at the.
What I don't understand is why that is a power law slope, but it's a power law slope across 2 orders of magnitude in precision.
I mean, what I see is something that could very well be a break and follow along and then deviate at the faint end. So, I mean, it's the deviation at the faint end, which you were pointing out rightly so, is it doesn't make a whole lot of sense, but you're doing an astrometric alignment when you're building the coads. So so in some ways you're recentroiding all of your sources in a way that is correlated across the image, but breaks my sort of assumption. Like I couldn't say offhand that I.
No, neither can I, because all I can do is make this plot. Yeah, that's why I'm here going, someone tell me. Mhm.
I mean, it wasn't released in any sort of general way, but if you're part of the project, you should be able to get to it. So what I would do is I would find, one of those coads, figure out the exposures that are associated with them, and look at all those images and look at the coad and see if it makes sense that it was put together
Mhm.
relative to the truth information that you think. And my guess is, since it's at the low end, it's that there's only a small number of photons in each one of them, and statistically you're just winding up shifted somewhere, especially after you do the re-registration. But there's really no way to tell just by looking at the catalog, I would say is my take. It was normal WFD simulation, I think.
So you're essentially saying that there's some, because I mean a log plot is an astronomer's cheat, right?
But
there's some break in there.
Restricted to some, WFD, but restricted to 20 square degrees or something, because we only had finite time. Yeah, I also interpreted that as a line and a break on the two ends.
Okay.
It could look like a power
Which
law
is
with two ends.
two different power laws, I guess, because it still is a power law, but it's only, but if it's, if
If you think about it as linear in a certain region, and then as you get to the two extremes, it starts to deviate, then.
Well, that's it in linear space. Definitely the faint end is a power law, but yes, there might be a break.
Anyway, my take on all of this
somewhere
is
there.
always you can't figure this stuff out just by looking at the catalogs. You have to go back and look at the images
Mhm.
because we're putting these pipelines together.
I mean, it's provocative, but I'm asking for help is essentially the conclusion. I don't know what's going on because yes, all I have is.
Okay, yeah, thank you. I think, yes, continuing this offline would be great. Thanks. Thanks everyone for coming. Maybe we can thank all our speakers once more.